For this example, we're going to look at an example of implicit differentiation, but it's not going to be the necessary way of doing it, just the easier way. So let's ask something along the lines of find all points on the unit circle such that the tangent line through the point goes through, let's say, 2, 0. I haven't tested this. I have no idea how awful the arithmetic is going to be. I can pretty much guarantee that it's not going to be a whole lot of fun. But when we do this, first of all, let's get a sense of the diagram. The unit circle looks an awful lot like this, only properly round, and then right over here is 2, 0. So 2, 0 does not lie on the unit circle, and what we are looking for are the tangent lines that go this way. There will be one over here, there will be one over here, and graphically that seems to be the end of it. There doesn't appear to be the chance of any other ones, so we expect to have 2 solutions. And obviously we can take over here y is equal to root 1 minus x squared. Over here y is a negative root 1 minus x squared. And we can plug our way through all of this awful lot of arithmetic and find the solution. But that just doesn't sound like an awful lot of enjoyable time to be spent, when we could just take x squared plus y squared is equal to 1. We could take the derivatives of both sides, and so we have 2x plus 2y, y prime equals 0. Y prime is equal to negative x over y. Let's take this point over here and label it as a comma b. And we know that a squared plus b squared is equal to 1. That doesn't need to be a part of your solution, but it's good to remember it. The a comma b fits this equation. And so at a comma b, the tangent has slope negative a over b. Just reading directly from above. Therefore, its equation is, and now we see the reason why we went with AB rather than XY. For the equation of the line, we're going to have an X and a Y, so we want to label the tangent line using some other letters. We want to use something else. We can go with X naught, Y naught. That's perfectly fine, but these days you simply don't get enough practice with having the same letter with different subscripts to make that feel very natural. So we go with AB, and so we have y minus b is equal to negative a over b times x minus a. Right, point slope form. And the point 2, 0 is on the tangent, meaning that we have y minus 0 is, sorry, that's the wrong bit. All of a sudden I put b is equal to 0, but I'm not allowed to play around with a and b. 2, 0 are points on the line. They're the x and the y coordinates. So let's fix that. Let's make it 0 minus b is equal to negative a over b times 2 minus a. And now we can bash this out and see what happens. Multiply through by b, or better yet by negative b, will give us b squared is equal to 2a minus a squared. And remember, a squared plus b squared is equal to 1. So I have b squared over here, b squared over here, every now and then you just get a nice bit of substitution, and so a squared plus 2a minus a squared is equal to 1. The a squareds cancel. A is equal to a half, and so b is equal to plus or minus the square root of 1 minus a half squared is plus or minus the square root of 3 over 4 is plus or minus root 3 over 2. And so our points over here at 60 degrees and at negative 60 degrees, those places, the 90-degree angles are going to give us our tangent lines, and those are going to meet right there at 2, 0. Some of the things geometrically are obvious, some of them are not. Because we go at 2, 0, we're on the x-axis for this point, we can expect, because of the symmetry of the circle itself, we can expect the x value to be the same for both of our points. That's not something that has to be obvious immediately over here, but it becomes obvious right there once the a squareds cancel and we end up with just a single value for a, no matter what it is that happens with b. And so once we've got this, the only thing that's left is to say the conclusion, the points are 1/2 comma root 3 over 2, 1/2 comma negative root 3 over 2. Let's shift that up so that it's actually visible, and we're done.